The Ermac Centre is proud to present the SFU Canada Research Chair's Seminar Series. This bi-weekly series hosts 5 presentations per semester. For the Spring 2011 semester, the presenters belong to the Departments of Biology, Physics, Mathematics, Chemistry, and the School of Resource and Environmental Management. Today's speaker is Dr. Nilima Nigam, Canada Research Chair in Applied Mathematics from the Department of Mathematics.
Good morning, everybody. So because of lots of competing events on campus, this is a little bit more intimate than it should be, I think. So I will keep my introduction much shorter. I mean, there's a very long version and there's the brief version which comes from Nilima, which is the only important thing is that she's here. And I certainly completely agree with that. Nilima got her PhD at the University of Delaware just at the very end of the previous millennium. And then she had an industrial postdoctoral fellowship at the Institute of Mathematics and Applications in Minnesota, where she worked with Seagate Industries. And so that's why the hard drives don't crash as much as they used to. And then she went to McGill and she received some prizes there, a very prestigious teaching award in 2005. And she also got an NSERC accelerator supplement in 2007, so that's very honorable. She joined us here in 2008 as a Canada Research Chair, and she was also quite strongly involved with MITACs in various capacities. She's interested in PDEs and numerical analysis. I don't go much more deeply in that. I would just say that she is a bundle of energy and a pure joy to have as a colleague. And as far as scientific talks go, I think you're in for a treat. And the title of her talk is At the Confluence of Exterior Calculus, Approximation Theory, and Numerical Analysis, High Order FEM Approximation in Pyramids, sponsored by the Egyptian Tourism Board.
The abstract was intentionally scary. And I'm following the principle that if you've braved the abstract, then you should be in for dessert. And if you came despite the abstract, well, then you should not be discouraged. It's better to be scared off by the abstract than to have a welcoming abstract and a scary talk. So this talk is going to be very heavily picture-based, right? And I'm going to divide the talk into 3 parts. And for the first 2 parts, I won't actually be talking about anything that I did. I'm going to be talking about what other people did. Okay? So I'm going to tell you what a PDE is. And many of you in the audience already know what a PDE is, but it helps to be reminded. I'm going to then tell you about what the finite element method is. And then only the final third of the talk, I'm going to tell you about how to design a pyramidal finite element. Okay? So what is a PDE? Well, a PDE is a mathematical description of a classical field theory. So you have some physical phenomenon or some biological or social phenomenon. You write down some rules describing what you're seeing, some mechanistic explanation. And if at all you can find a continuum quantity in there, which is the object that is going to be modeled, you're probably going to end up with a PDE for it. PDEs are therefore a very elegant framework for studying our world, whether it's the physical world, our social world, our biological world, our technological world. PDEs end up being pretty much anywhere you can think of. More technically and jargonfully, if you have a function of some spatial variables, an unknown quantity u, and a certain finite number of its derivatives in space or whatever other independent variables you might have, then trying to solve an equation of that form leads you to the solution of a PDE. Okay? So this is a very, very abstract setting for PDE. It includes nonlinear PDEs, it includes systems of PDEs, whatever. So I was thinking about how to structure this talk, and I thought, well, I could launch right into numerical analysis. But that's not helpful. So let me go back in time and think about where it all started. So I think the first PDE that was officially written down was written down by D'Alembert in 1752. And he was interested in studying the motion of a vibrating string. So that's the 1D wave equation. It's the first known PDE because it had two independent variables, time and space. Then in 1755, Euler, who was interested in writing down the motions of incompressible fluids, wrote down the Euler equations. And that picture over there is a very famous cover of the album of fluid motion, which I highly recommend everybody should own a copy of. It wasn't until 1959, and then subsequently in 1762, that the wave equation for 2 and 3D were written down, and they were written down for acoustics. So Euler and Bernoulli generalized what D'Alembert had done to 2 and 3D. And then in 1760, Lagrange wrote down the so-called minimal surface equation, and the structure you see there is a minimal surface under certain constraints. So if you've taken a PDE course, there's something odd here. You see the wave equation, you see the equations of incompressible fluid flow. You don't yet see the Laplacian, right? The Monge-Ampere equation, which Brittany spoke about, is tattooed on the guy's forearm on the top. And it was written down by Monge in 1775. What we call the Laplacian, or Laplace's equation, was not actually formally written down in that form until 1780. So nearly 30 years after the first PDE was written down. But this is the first one we tend to study. The heat equation, well, it was another 42 years before that was written down. And this was thanks to the Fourier's law of cooling. And then there was a whole profusion of modeling activity in which lots and lots of people who were interested in mathematical physics started to write down mathematically what they already knew from physical laws. And so, for example, in 1822 through 1845, the equations for fluid flow were written down in the form of what we now call the Navier-Stokes equations. So since then, of course, there's been lots of science, there's been lots of math, there's been lots of mathematical science, there's been a lot of scientific math. For example, in the top left corner is the first time Schrödinger's equation was written down. Okay, so the little white box there is an excerpt from Schrödinger's paper in Phys Rev in 1926, which is now the foundations of quantum mechanics, if you will. In 2007, people were interested in writing down equations for cell motility. So cells move, and how do they move? Well, you can write down equations for those. You could describe the motion of people in neighborhoods. This is on the left. Whoops, on the left is the cover of PNAS from 2010, and it's work by Brantingham in which he's showing some crime hotspots. And these are results of writing down social behaviors in the form of a PDE and then simulating them. You can model financial markets. You could work with Steve Ruth and study PDEs and surfaces. You could design art. You could have these magnetic coils that discharge what looks like electricity in the Tesla coils. All of these are examples of PDEs. These are all things for which you can write down PDEs. You can write down PDEs for the growth of clouds. You could write down PDEs describing the motion of black holes. And just to give you an example of the kinds of cool things you could do, or I think they're cool, here's a list of the projects I've been involved with over the past decade. So carbon nanotubes, the Poisson problem, Maxwell's equations, linear elasticity, nanoelectronics, crystallization, scattering. Right. So it's all attention deficit disorder until you realize that it's not really. My training was in PDEs. And as Poincaré says, even though the equations that describe what you see in mathematical physics and much of the other sciences look very different, the boundary conditions look really different, there is a strong family resemblance between what you see. So even though I could be talking about the heat equation on the one hand and the Laplacian on the other hand and electrostatics on the third, these seem to come from different parts of our experience, but mathematically, they're all very, very related. And so if you think about it just at a distance from what it is you're modeling, it's really not that different. So if you understand the underlying PDEs, you can access a lot of very rich phenomena that we see out there. So this is a very exciting time to be a mathematician, because if you're willing to talk to scientists and you know your math, odds are that you will find something familiar in an unfamiliar application. All right, so this is all very well and good. You've got all these PDEs, you've got all these phenomena, you've got all your collaborators, but ultimately you actually have to solve this beast, right? So a PDE is good, it's descriptive, but it's not particularly useful until you can tell us something about the underlying field. And so we hammer into our students various techniques for solving PDEs. I put solve within quotes for a reason. You could use separation of variables in some contexts to try and get your hands at a solution. You could use complex analysis techniques, you could use the method of Green's functions, etc. There's a long list. And all of these methods are trying to get at either the analytic solution or a really good approximation to it. But the one at the end, numerical approximation, that's what I'm interested in. And the bulk of science today is driven by that last category. Okay. So we're going to be focused on that. And in particular, we'll be focused on one particular numerical approximation strategy, the finite element strategy. So I have to tell you about this. So here's a little example. It's a toy example. It's not even a PDE. It's an ODE. So it's a two-point boundary value problem. And I'm going to try and find a U so that the concavity is specified on the interval -1 to 1. I need to pin down the boundary conditions. So I'm going to say that my field is going to be 0 at both the endpoints. And I want to avoid pathologies. So I'm going to insist that both U and its derivative be finite in some sense. So I'm going to insist that the square of U be integrable and that the derivative of U be integrable. Okay? This is just to avoid pathologies. A short form for the statement that U vanishes on the boundaries and that it has bounded square integral and square gradient integral is that U is in this red set. I'm going to call it H10. Okay? It's a set of finite energy somehow. Another way of stating the problem that I'm trying to solve is to frame it in terms of minimization. So I can write down a function j of an arbitrary function w, and the function looks like 1/2 of the square of the derivative of w minus the prescribed function f times w integrated between -1 and 1. If I minimize this, the minimizer, under some other conditions, will solve the BVP. Conversely, if I can solve the BVP, it's going to be a minimizer. Okay? And you can use the calculus of variations to write down a consequence of the minimization problem. So if you pick any arbitrary function v in the admissible set, then if you can solve, there are primes missing in the bottom thing, if you can solve the equation at the bottom with primes on the u and the v equals fb, then you're going to be able to solve the minimization problem, which in turn tells you something about the BVP. Okay, but in practical terms, I can't actually do this, certainly not by hand. So what I'm going to do is I'm going to seek approximations. I'm going to say that the candidate that I'm looking for, u, is actually going to be well approximated by something I call u sub h. H is going to be a parameter here. And u sub h is simply a linear combination of some functions phi sub I. I get to pick the phi sub I. Okay? And if I plug this into my problem that I'm trying to solve, I get a discrete problem which is now finite dimensional. And the unknowns in the problem are precisely the coefficients c sub I. Okay? So here's the toy example done out again. I take the interval from -1 to 1, and I subdivide it. I don't have to pick equal subdivisions, but for this example, why not? So I put down a whole bunch of points on the interval from -1 to 1, and they're spaced h units apart. The object c sub I, phi sub I is going to look like a little triangle. So it's going to be 0 for most of the interval, and it's going to be like a little hat function with height ci at grid point xi. Okay? So I'm going to try and use a whole bunch of these hat functions, add it together to approximate my solution. And if I do this, hopefully this is what I get. Okay? Now, how I precisely get my hands on the CI is the matter for a different talk. That's linear algebra. But let's say I could do this. Well, this looks kind of promising. It looks a little jaggedy, but all right, maybe I'm on the right track. I could conceive of adding more grid points, so more of the yellow points, more hat functions, and hopefully if the method is a good one, then I'm going to get a smoother and smoother curve, right? So we have a good method in some sense if shrinking the distance between points to 0 leads to a better solution u. Wow, does this work? It does. So on the left, I've overlaid, or Doug Arnold overlaid, the true solution of this boundary value problem with a computed finite element solution. You can't see the difference, right? They're completely on top of each other. But just to convince you that we haven't cheated, that there's actually some approximation going on here, on the right is plotted the derivatives of the computed solution. Now remember, we were approximating by things that look like hat functions locally. So the function, the u sub h that we get, really has a bunch of piecewise linear bits. If I take derivatives of piecewise linears, I'd better get step functions, right? And that's exactly what you see. You see a little staircase in green. That's the approximation to the derivative, u sub uh prime. And the true derivative is plotted underneath it. Okay? So the method that I just constructed gives us the quantity that we want, which is on the right. And we haven't just plotted the exact solution and nothing else. You can convince yourself by looking on there. Okay, so approximation theory is the study of how to get even closer to the true solution. I could add more points. I could change the basis functions. I could use things other than hat functions. I could use curvy functions. I could use piecewise quadratic functions, cubic functions, trig polynomials, whatever. There's a zoo of functions I could use. So in particular, in the finite element planet, there are two kinds of things one might try to do. On that side, under H refinement, you're trying to approximate the solid line, which looks like a little bendy curve. And you could either approximate it by taking 2 points and drawing a straight line between them. Or you could add a third point and draw piecewise linears. So you get something that has a kink in it. And you can imagine that as you add more points, you're going to get closer and closer to the solid line. So that's one form of approximation. You add more mesh points, you hopefully get closer. On the other hand, you could fix the number of grid points you have. So you take 3 grid points, or really 1 interval, and you either work with a piecewise linear, so you have just one straight line, or you can try and approximate on that interval with a quadratic function. So increase the degree of your basis function. Okay? And you can see that you get very, very close very, very quickly. Both of these are legitimate, both of these are useful, and both of these are necessary in different contexts. Okay? So just to hammer in the point, if you were using piecewise linears as your basis functions, you would have on an interval 2. So you'd have half the hat function for the one and half the hat function for the other. If you were working with quadratics, you'd have 3 basis functions on any given interval because you have 3 degrees of freedom to pin down. Right? So you could try the same problem again. And now this time, let's do it a little differently. So the same boundary value problem. This time, I'm going to introduce an auxiliary variable. I'm going to write down sigma as the derivative with a minus sign. And if I plug that into the original ODE, I get sigma prime is equal to f. So now I have a system of equations. They're first order. This is how I rewrite my ODEs to feed them into MATLAB. MATLAB knows how to solve first order ODEs. So if I have a second order ODE, I introduce auxiliary variables and then I go from there, right? So okay, so I've taken a second order ODE, reduced it into a system of first order ODEs. I could do the same thing that I did before. I could write down the weak formulation of this problem. In this instance, I have 2 equations. So I have to minimize the one and maximize the other. So this is a saddle point. I'm trying to find the saddle point of the system. And I need to find my sigma in the space of finite energy as before. And I need to insist that U has a square integral. That's the only conditions I need to enforce. This is called a mixed method. And I could do the same thing that I did before. I could seek a discrete approximation. So I'm going to seek a discrete approximation for the U and a discrete approximation for the sigma. And there's nothing tying me down to hat functions for both. I could choose phi sub i's for one and psi sub i's for the other. Okay. So that's the system that I have to solve discretely. It's a saddle point problem. It's finite dimensional. How I solve it? Go take a linear algebra class. How do I pick my basis functions? This is an approximation theory question. Okay? I could do a lot of different things. I could pick the same kinds of basis functions. I could choose piecewise constants for U. I could choose piecewise linears for the sigma. I could choose piecewise linears for U, piecewise cubics for sigma. Many, many combinations. So let me try these 2. Let me try piecewise constants for U and either piecewise linears or piecewise quadratics for sigma. Okay. Which do you predict is going to work better? Remember, quadratics are supposed to do a good job of approximating, right? So if I have the fixed number of mesh points and I increase the degree, I should do better, right? Yeah, Karen will not be led astray. All right, here he goes. If I chose piecewise constants and piecewise linears, I've got the colors backwards. So if I choose piecewise constants for U and piecewise linears for sigma, I get the curve that should be in green. Okay, and it does okay. It does okay. So on the left, I've got the approximations of the U, and on the right, I've got the approximations of the sigma. But if I choose piecewise quadratics for the sigma, then I get all these oscillations. I'm not approximating what I want to approximate, even though I'm choosing a high degree polynomial. In fact, if you look back at U, I'm really under approximating the U. So the choice of approximation spaces for the one field cannot be made arbitrarily and distinctly from the choice of approximation for the other field. Okay? This is disturbing But okay, let's forget about it for now. And let's go back and ask ourselves, formally, what is a finite element? So a finite element is really a triple. It consists of a domain. So in the example that I showed you, it was a little line segment. A function on that domain, so a collection of these basis functions gives me a finite dimensional vector space. So think about the hat functions. And then a set of linear functionals that allow me to specify values in that vector space. And so here's what we've seen already. So if you had a little line segment, you could pin down the values of the function at two endpoints, right? That's the simplest way to specify a piecewise linear. That's the simplest finite element you can think of in one dimension. On the triangle, you could specify values on the nodes of the triangle. You could mesh a region in space with rectangles. If you're in 3 dimensions, you could mesh with tetrahedra. You could mesh with bricks. You could mesh with prisms. You could mesh with pyramids. Okay. So how would this work in 2D? Now I'm going to go through the same exercise, but in 2 dimensions, and I'm going to go a little faster. Okay. So I'm going to try and solve the Poisson problem in 2 dimensions. I write this in variational form. So I write down the equivalent minimization problem, and then I write down the variation. And I'm going to try and solve it on a bit of a pie that's been eaten away. So anybody that's suffered through a numerical analysis class with me knows this example. I'm going to be solving it on 3/4 of a circle, and I'm going to approximate 3/4 of a circle with lots and lots of triangles. And on each triangle, I'm going to pick a basis function. In fact, 3 basis functions. So that's my mesh. I've taken the region I want to solve my PDE on, and I've discretized it using mapped versions of the same element. Then I'm going to write down a discrete approximation. I get a discrete linear system, and if I solve it, I get something nice, provided in this instance I've taken the solution that has mean 0. Okay? So I can actually solve this problem. I probably could do it by hand, but it's painful. Now, that's one kind of problem, but problems in physics come from everywhere. So maybe I need different kinds of differential operators, and maybe I need different notions of energy. And on this slide, I've tried to combine some typical notions of finite energy. What we mean by energy changes depending on what problem we're looking at. So if you're looking at Poisson's problem, it suffices to look for functions u whose gradients are finite in some sense. If you're interested in electromagnetics, you might be interested in vector fields whose curls are finite in some sense. You might be interested in fluxes, in which case you want the divergence of those vector fields to also be finite. Or you could just be interested in objects in L2, so you don't care about their derivatives. Here's an example where I'm going to try and show you all those different function spaces in action. Stokes flow through a pipe. Okay, so I've got a pipe with a square cross-section, and I put a pressure gradient across it. And I specify that the fluid's incompressible, and that I tell you what the tangential components of u are on some parts of the pipe, and I tell you what the normal components are on other parts of the pipe. This is not the only way to solve that problem. However, you could do the exercise that I did before. You could write down an equivalent energy problem. It's going to turn out to be a saddle point formulation. You can write down the variation of that, and this is what you get. You get a system of 3 equations. And the unknowns that you're looking for, well, now one of them has finite curls, so it comes from H curl. One of them has finite divergences, so it comes from H div. And the third comes from L2. Okay? So this is a system of equations in which the three unknowns that you're looking for come from different function spaces. Okay? And how would we pick approximation spaces for these guys? We already know that if we make just arbitrary choices, it may work, it may not work. There's got to be a systematic way of thinking about this. And indeed there is. The finite element theory began, I would say, in the 1960s. And since then, people have used the finite element method to study a whole host of PDEs. And in the study of a whole host of PDEs, they've come up with a whole zoo of finite elements. Okay? So for example, on the tetrahedron, you could specify point values on all the nodes of the tetrahedron. That's the so-called Lagrange element, and so it's on top. You could specify the value in the middle. That's a so-called discontinuous element. You could specify tangential components on the faces of the tetrahedron. You could specify the normal components of a vector field. You could do these for many, many higher order objects. So if you look in the literature, there's literally tens of thousands of papers on finite elements. Each of them has either developed one of these or used one of these or said, don't use this, use these other ones instead. And if you have a multi-physics problem, you need to pick from the set, combine, and then work. And it gets hard. It gets hard. It's not always obvious that you've made good choices. So for almost 40 years, this was both a science and a bit of a black art. How do you pick finite elements, particularly if you have a mixed problem? It wasn't until 2006 that this famous paper by Arnold, Falk, and Winter wrote down something systematic, a sort of meta theory for finite elements. And what they said was, well, let's go back and look at what the geometers have done. The geometers have something called Hodge theory. Let us think about what these PDEs are. These PDEs involve derivatives, curls, gradients, divergences. These are not random objects. These have some very, very deep meaning associated to geometry. And so if we're going to be discretizing there, we might want to respect the structure that comes with the geometry. So this confluence of Hodge theory with finite element theory is what is now called the finite element exterior calculus. And so in a nutshell, and very loosely speaking, our favorite spaces, the things we like to work with, they form something called a de Rham complex. Okay? Functions in H1, if you take a gradient of them, it will turn out that they're actually in H curl. If you take an object in H curl and you take a divergence of that, it'll turn out that you'll end up in H div. And if you take a divergence of something in H div, you're going to end up in L2. More than that, the ranges are closed. And even better, if you take the curl of a gradient, you get 0. You take a divergence of a curl, you get 0. So this sequence is exact. Has nothing to do with PDEs. As long as your region omega is smooth, it doesn't have holes punched into it, doesn't have weird boundaries, the sequence is exact. Okay? It's a beautiful fact. And numerical analysis, people kind of knew this, but didn't really care. Physicists knew this stuff. They knew that if you were in H1, you were working with something called a zero form. So if you were thinking about potentials in electrostatics or temperature, these are zero forms. If you're thinking about electric fields or magnetic fields, these are one forms. Their curls have to be finite. If you're thinking about fluxes, they are two forms, and their divergences have to be finite. So independently of the geometers, physicists sort of knew that if you specified fields in different physical contexts, they had different properties as vector fields. And In 1957, a geometer named Whitney was trying to prove a theorem. He was trying to understand inherent properties of manifolds, and he said, well, if you have the exact sequence above and you triangulate the manifold, you can write down a set of discrete forms that also have an exact sequence property. So if you take a tetrahedron and you specify the values on the nodes, and then you took a gradient of that, it's going to give you something whose tangential components you can actually measure, and so forth. So what you have in this purple box is a discrete exact sequence. This is the lowest order discrete exact sequence for the de Rham complex, and it was discovered by Whitney way back in 1957. And what's marvelous is that this little box sat in the literature from 1957. This box here, with all these other elements, were around for another 40 years, but people weren't reading the same literature. So if you stare at this box that I just pulled up, you can see that the Lagrange elements, the Nedelec edge elements, and then the face elements of Nedelec, and the discontinuous elements. These are precisely what's sitting in the Whitney complex. So finite element people had already discovered some of these elements on their own. And they had said that these things have nice properties for doing certain problems, but they had never put that together with what the geometers knew. And that's why it's a really marvelous intellectual achievement to put together these two strands of human inquiry and come up with the so-called finite element exterior calculus. Okay? Because what Whitney did was very systematic. It is exactly the discrete analog of what happens at the continuous level, and it gives you finite elements. Okay, so in a nutshell, if you want to build a new finite element, make sure it approximates the spaces in the continuous complex. Make sure that the discrete spaces themselves form a sequence. You take a gradient of a discrete object, you should end up in the next space, and so forth. And make sure you can go from the continuous functions to the discrete ones in a bounded manner. So make sure your interpolants are bounded. Haven't started my talk yet. So here's my talk. I'm interested in writing down finite elements for the pyramid. Okay. Why the pyramid? Let me first back up. The finite element method is incredibly successful. If you want to study weird kinds of problems in 3D, you can go out and purchase commercial software, you can find freeware. Most of these methods will have either tetrahedra or bricks meshing your geometry. You can study problems that range from heat exchangers through fan blades, through I don't even know what that is, through hearts. You could do all kinds of crazy things. So why a pyramid? Well, okay, here's an example of a heat sink. Okay, so this is a bit of a heat sink, and some engineers wanted to study the properties of this heat sink, and so they were going to use the finite element method. So they were going to discretize it using tetrahedra and some boxes. So they're going to use bricks along the pipes. And if you zoom in, you have bricks in green, you have tetrahedra in purple, but to talk to tetrahedra, you need to have triangular faces, and to talk to a brick, you need to have a square face. And you're going to need some objects which have 4 triangular faces and one square face. These objects are precisely the pyramids. Here's another example from the same research group. This is an electromagnetic device, doesn't matter what it is. they found that when they were trying to use a finite element method here, it was incredibly efficient to use bricks for some part of the domain and tetrahedra for others. They were able to cut the number of degrees of freedom down by a factor of 10%, which is a lot. And if you zoom in, again, between the bricks and the tetrahedra, you find pyramids. Now, the technology has been developed theoretically and in the engineering literature for tetrahedra and for bricks, but not for pyramids. Okay, so this is an engineering concern, but that's not my concern. Well, it should be my concern, but it wasn't. Until I met Leszek Demkowicz, who said that a successful finite element method for Maxwell's equations, that's in 3D, needs to have the facility to include tetrahedral objects, pyramidal objects, brick elements, and prisms. Of these, pyramids were very, very hard to work with. And he even suggested that one must go to the new theory of the finite element exterior calculus to develop these finite elements. But nobody had done it. Here are the ground rules. We're going to be taking pyramids, and we want them to talk through their faces with whatever comes next to them. So next to the triangular face of a pyramid comes a tetrahedron. Next to the square face of a pyramid comes a brick. I want them to do a good job of approximation, so these need to be high-order elements, and I need them to satisfy an exact sequence property. So these are the ground rules. There have been attempts at the pyramid before. So Bedrosian in 1992 wrote down the first and second order elements for H1 on the pyramid. Other attempts since then have taken the pyramid and broken the pyramid in half into two tetrahedra. That works unless you think about it and notice that on the square face you end up with an edge. But on the brick you don't actually have that diagonal edge. So you're not allowed that edge in a conforming method. So to recap, that's what I want to do. I want to find spaces V0, V1, V2, V3, which approximate the spaces H1, H curl, H div, L2 in such a way that they form an exact subcomplex and that I can find interpolants pi0, pi1, pi2, pi3. Some work's been done on other elements of the sequence. So Graglia proposed first and second order edge and face elements, but he didn't actually show or care that they satisfied the sort of exact sequence property. Ralph Hipmeyer in 1999 with his co-worker Gradnaru showed first order elements for the whole sequence, but not higher order elements. There's the work of Sabina Zagelmayer, which has never appeared in the public domain. She apparently has found high order elements on the pyramid using a different approach altogether. And here's why it's difficult. Here's a challenge which makes the pyramids both interesting and hard. So there is no high order conforming element consisting only of polynomials. So on the brick, you can have polynomial basis functions. On the tetrahedron, you can have polynomial basis functions. On the pyramid, you cannot do the job with just polynomials. Okay, here's why. Let's take a pyramid. Let's take the function u, which I've written down above. That function looks like it's got a singularity at z equals 1, but in fact, it doesn't. If you look at it carefully, it doesn't. It's got a square integrable first derivative. So this object is in fact an H1. Okay? And moreover, u vanishes on 4 faces of the pyramid, and on the triangular face y equals 0, u becomes a polynomial. Okay? So u is a function which is 0 on 4 faces of the pyramid. It's a polynomial on the other one. And this suggests that, well, maybe there are polynomials out there which can approximate and match up with you in the interior. Okay? So let's try this. Let's look for a polynomial P which has the same values on the faces as you and is polynomial throughout the pyramid. Okay, so it's got to have the form that I've specified. It's got to vanish on the faces x equals 0, z equals 0, x plus z equals 1, and y plus z equals 1. And then you've got a remainder factor, which has got to be polynomial. I insist that P is polynomial. And then I look at what happens on the face y equals 0. Well, if I look at what happens on y equals 0, I must conclude that one of the terms in my polynomial is actually the fraction 1 over 1 minus z. Okay? So there is no way to write down the polynomial P so that it matches all the faces, on all the faces it matches you, and is yet polynomial throughout. Okay? So you have to expand your notion of basis functions here. So that's one worrisome thing. The other worrisome thing is the following. You might think, well, here's a design principle. I know exactly what to do on a brick. So let me specify the finite element on the brick, and then let me map the brick to the pyramid. And I can do that by taking the top square face and squishing it down to a point. Okay, so you can see the level sets there have become the level sets in the pyramid. And this transform is precisely the Duffy transform. And here things go wrong again. Here's why they go wrong. When you map the cube to the pyramid, then the functions in the various function spaces you're interested in will also map, right? You've got a function on the cube, it's going to turn into something on the pyramid. But it matters what kind of function it is that you're working with. The transformation rules are different for different functions. So if you, for example, have a function in H curl, you're going to pick up the Jacobian of transformation. Okay? It's not just a matter of changing the x and the y and the z coordinates. You actually have to change the form of the function. Again, this is something that was known to the physicists. So if you're working with objects in H curl, then you want to make sure that tangential fields are always continuous. That's the only form of continuity you're allowed. If you're working with HDiff functions, then they always have to have continuous normal components. Okay? That's why electric fields cannot become tangential at the surface of a perfect conductor. And that's why magnetic flux lines can't go normal into an object that is magnetic. Okay, so we need the finite elements to patch with their neighbors, following the rules that I have in the table. And I know that on the tetrahedra and on the brick, I have polynomials. But if I use a Duffy transform, I can't actually do this. So this is deeply disappointing. Okay. And this is where Joel made this incredible breakthrough. So he said, well, rather than mapping a pyramid to a cube, let's map the pyramid to a semi-infinite box. He calls it the infinite pyramid. So you take the vertex of the pyramid where 4 triangular faces meet, and you pull it all the way up to infinity. And if you do that, you get something that looks semi-infinite. And it's going to have the symmetries of a cube. It's going to have hexahedral symmetries. You've got to worry about the fact that you're zooming off to infinity in one direction. So you can't work with polynomials. You're going to have to work with rationals. But that's okay. You're going to work with these k-weighted polynomials that I've denoted by q sub k lmn. They're polynomial in the 3 variables x, y, z, and they're weighted by 1 plus z to the power k. So let's think about what's going to happen here. If I take the polynomial x on this pyramid, and I map it to the finite pyramid, that's not going to work. Because at the vertex, the value that I get will depend upon the path that I choose to get there. So I have to throw polynomials like x out of this problem. However, I need to keep functions like z to the k over 1 plus z to the k. Because when I map them back to the finite pyramid, I actually need to keep objects like that. So here's what our first guess is at approximation spaces for h1 functions. These are rational polynomials on the infinite pyramid. And then I'm going to make sure that if I take gradients of these objects, I get into H curl. So that's my guess for my H curl conforming elements. That's my guess for H div. You're not going to remember this. You don't need to remember this. The point is, if I know how to write down the H1 element, I should be able to use the exact sequence properties to construct the rest. And I insist that the spaces match up with their neighbors in the correct fashion. I can then pull back these objects to the finite pyramid, and I've built in the correct patching conditions by construction. Okay. These are arbitrarily high order. You pick a P, I can give you an approximation space that is, in fact, even contains the polynomials of degree k in there. I can specify degrees of freedom in a nice way. And if you know what a Helmholtz decomposition is, this is a nice property. I actually have an exact sequence property. And this is just by construction. Okay? I can define bounded interpolants. But here is a subset of those approximation spaces where you can see very clearly what is going on and why these things are so beautiful. Start off with an approximation space for H1. I know that if I take a gradient, I need to end up in H curl. So let me take a gradient. Look at that. So part of the approximation space for H curl consists precisely of the gradients of the objects in H1. Let's try this again. So I know that if I take the curl of the gradient, the second set's going to drop out. But what happens to the curls of those guys? Those had better be in H div. Well, look at that. They're right there, by construction. If I take the divergence of the curls, I'm going to drop out. So I've got to work with what's left. And the divergence of that set had better be in L2. And whoa, there we go. So by construction, these sets form an exact sequence. There we go. And so let's come back to that highly contrived example, which you would probably never use finite elements for, and you would probably never write down this particular mixed formulation for, but anyways. That's the mixed formulation. In operator notation, that's what it looks like. Okay. So you can see the very particular structure there. And so we take the square pipe and put in 8 boxes, so 8 boxes, and each of them is subdivided into 6 pyramids. And then we use the pyramidal elements to try and approximate the true solutions in there. And so what you see are profiles at the cross-section x equals 0.3 of the field U. And then, I don't know if you can see the error bars here. So these are the absolute errors in U and in W. This is the more interesting plot. So you can actually see that if you compute the error and you increase k, then you do a better and better job of approximating the solution. So the error goes down as you increase the order of the approximants. All right, so I'm done. I constructed high-order conforming finite elements using an exact sequence property. And they satisfy this beautiful commuting diagram property. And I know for a fact from the finite element exterior calculus that these are going to be exactly the right sets of things to use in mixed problems. Okay? So I'd like to thank NSERC, the Canada Research Chairs, and MITAX and FQR&T for letting me futz around with this. This is work that's taken about 5 years. And very few people, apart from my mom, have that kind of patience. And I, of course, owe a debt of gratitude to everybody that's ever taught me anything, my students, and, of course, the recently minted Dr. Joel Phillips. So thank you.
Well, thank you very much. Are there any questions?
Just for curiosity, how much of this is used or in higher dimensional analogs of what you've told us?
Excellent question. So people that are starting to look at numerical gravitation, for example, are studying higher dimensional analogs of these. But the technology there is still, I mean, it's much more theoretical work has been done than practical work. But indeed, yes, people have started looking at higher dimensional analogs. You can also look at different complexes. So the Durham complex is not the only one. You could look at the elasticity complex or the Dirac complex.
One quick question. So in a way, it forces you to get to rational functions kind of thing. And so
well,
in some ways, why not use, I mean, and has that been tried, use rational elements? I mean,
so these are precisely, these are in fact rational elements. So when you look at what these approximation spaces on the pyramids are, we end up with rational functions. So we see that the set of rational functions include polynomials as a subset, but the basis functions are rational.
And
use rational elements
on other elements. Has that been sort of pursued in any way? I mean, or not found to be necessary?
On other elements, you can get away with polynomials. And polynomials have such nice properties, right? It's very easy to differentiate them. It's very easy to integrate them, etc.
One more division and you got rationals.
Then you have to do quadrature.
Well, then let's thank Nilima one more time. And